Hi, I'm Lauren Coombe from Canada's Michael Smith Genome Sciences Centre at BC Cancer in Vancouver, Canada. And here I'm presenting my poster, GoldRush-Link, integrating minimizer-based overlap detection and gap filling into the ntLink long-read scaffolder. So GoldRush-Link is an essential step in our new de novo long-read assembler called GoldRush. And the step is powered by our ntLink long-read scaffolder, which was published last year. So with GoldRush in mind, we introduced a number of new features and improvements to ntLink, including overlap detection, gap filling, and liftover-based rounds. So before describing these new features in a bit more detail, I just wanted to give a brief background about minimizer sketches, since minimizer sketches are quite important to ntLink in general, as well as some of these new features. So in generating minimizer sketches, for each window of W adjacent k-mers, we compute hash values of each k-mer, and the window will be assigned to the smallest hash value. So repeating this over the sequence then generates an ordered list of minimizers per sequence, and that can be used in ntLink's case to map sequences to each other. So first, just a note that the schematics describing the different features will use these orange boxes for context sequences, gray lines for long reads, and the circles for the minimizers where the same color indicates identical minimizers. In previous versions of ntLink, when there were two sequences to be joined that had a putative overlap, they would still be joined end to end, and that could create this duplicated region by the join or this small insertion misassembly. So to avoid that, in these cases, we now use the overlap detection feature where we look for minimizers that are in common in that overlapping region, create an undirected minimizer graph, which we filter and traverse to come up with an anchoring cut point minimizer. We then trim the incident sequence up to that cut point and join the trim sequences together. And that avoids inducing this duplication or this insertion at the join point. So now moving on to describing the new gap filling feature of ntLink. So in earlier versions of ntLink, when the evidence was used to join sequences together, we would insert a gap or sequence of ends between those sequences. And so with this gap filling feature, we endeavor to fill those ends with actual ACTG sequence instead, which can be helpful for downstream analysis. In the pairing stage, ntLink maps reads to contigs using minimizers and then uses that evidence to decide what sequences should be put together. But for gap filling, we use those same mappings, but just now in deciding what sequence should be added into the gap. So we choose a representative read to fill in the gap. We remap it to the contigs using a lower K and W, just giving us a bit of a higher resolution and helping us to find anchoring minimizers or minimizers in common between the read and the sequence that are closer to the gap region. Once we find those points, we trim the contigs up to those minimizer points and then use those to find what region of the read should be filled in the gap sequence. And that gives us our final scaffold with a filled gap sequence. Do note that the gap is filled with the raw read sequence, and so we would recommend downstream polishing. The final new feature I'll describe from ntLink is the liftover base rounds. So we find that running additional rounds of ntLink can produce more contiguous final assemblies, but remapping the reads at every round is quite costly. So what we do is we have the input draft sequences, do one mapping of the long reads to the draft sequences, continue the rest of ntLink, but then before the next round, we just use the composition of the scaffolds to lift over the coordinates of the ntLink mappings and continue the round from there. So now moving on to some results, first focusing on the overlap detection and gap filling features. So we used Oxford Nanopore long-read data from two different human individuals in testing ntLink. For individual NA24385, our baseline assembly was GoldRush GoldTigs. GoldRush GoldTigs being polished and correcting golden path reads from our GoldRush assembler, and the golden path just being about a one-fold read representation of the genome. For individual 19240, we used a Shasta assembly as the baseline. So looking at the plots on the right part of the slide, you can see that we have a contig and scaffold NGA50 length on the y-axis. So NGA50 is very similar to NG50, which means that at least half of the genome is in pieces, at least the NG50 length, and NGA50 is just adjusted for misassemblies. And then a contig NGA50 is only distinct from the scaffold counterpart because it is first broken at end sequences. And so on the left-hand plots, we can see the contig NGA50 length versus the number of ends per 100 kilobase pairs. Here we want to be in the top left of the plot. And you can see that using both the overlap and the gap filling features of ntLink, we have a substantial reduction in the number of ends. So we're doing well with gap filling and a really big increase in the contig NGA50 length for both individuals. On the right-hand plots, we're looking at the scaffold NGA50 length versus the total number of misassemblies. And once again, we want to be in the top left corner. And we can see that generally using the overlap feature and then also the gap filling feature, we see a reduction in misassemblies and the scaffold NGA50 length stays quite consistent. And now looking at some results from running the liftover-based rounds of ntLink. Here we're using the same data as in the previous slide. On the left-hand plots, we're looking at the scaffold NGA50 length versus the number of rounds. And you can see as we do additional rounds of ntLink that we are getting pretty good increases in contiguity, and that actually we're seeing better increases in contiguity from using the liftover rounds versus the naive full rounds. And on the right-hand side, we can see that running the liftover rounds does give us a substantial time savings compared to the full rounds. So in conclusion, multiple new features were added to the ntLink long-read scaffolder, which were overlap detection, gap filling, and liftover base rounds. While these improvements were made with our de novo long-read assembler GoldRush in mind, they're also applicable to the general usage of ntLink. Thank you for listening to my poster presentation. To try out our tools, check out our GitHub page, and to learn more about the GoldRush long-read assembler, check out these posters and talks from my colleagues.